Emission and absorption spectra. Heated objects emit electromagnetic radiation. The higher the temperature, the more radiation is emitted, and the proportion of energy emitted at different wavelengths varies, as given by Wien's law. The range of wavelengths given off is called the emission spectrum, and can be one of three types: line spectrum, a band spectrum, or a continuous spectrum. What we get depends on the material being heated. First, line spectra. These are produced by individual atoms, as we'd find in gases under low pressure. They contain only certain well-defined wavelengths, and when passed through a diffraction grating, we get a pattern of lines from these well-defined wavelengths, rather like this. This is the line spectra of hydrogen. These lines are specific to an element, so helium, for instance, would have a different line spectrum. This acts like a fingerprint and allows scientists to determine the element emitting the radiation. Further details of how line spectra are produced can be found on the video named Ionization and Excitation. Band spectra. These are formed by gases whose molecules contain more than one atom, like the diatomic molecules oxygen, nitrogen, etc., as well as things like carbon dioxide, carbon monoxide, water, and so on. They consist of separate groups of lines or bands of lines. This, for example, is the band spectra of oxygen. You'll see we have a band of reddish lines, a band of greenish lines, and a band of bluish lines. And now continuous spectra. These are produced by hot solids or liquids, or by high-pressure gases such as found in stars. They consist, as the name suggests, of a continuous range of wavelengths, and give a pattern rather like this. Now on to absorption spectra. Now, an absorption spectrum can be either line, band, or continuous, but they're formed, as the name suggests, by the absorption of certain wavelengths of radiation. Here we have a star consisting of high-pressure gas in the center, which will produce a continuous spectrum. But as we move further out, we end up with a low-pressure gas in the atmosphere, and low-pressure gases would form a line spectrum. To understand how absorption spectra work, it's easier to use a model something like this. Here we have a group of photons representing all the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet, which are heading for an observer over here, but must first pass through a region of low-pressure gas here. Now, most of the photons do not have the correct energy to excite electrons within the gas, and so will pass straight through and be seen by the observer. The green photon, however, will excite an electron in the gas and be absorbed, like this. Now that green photon's energy is held within the gas, and that will very quickly be released, but it could be released in any direction, so it could go over here, for instance, or head back almost the way it came, and is highly unlikely to reach the observer. In this simple model, this is what would be observed. We get the red, orange, yellow light coming through. We don't see green, but we do see blue, indigo, and violet. In reality, it's much more specific wavelengths that are removed, and we see something like this, with certain lines. So in effect here we have a line spectra superimposed on a continuous spectrum. The continuous spectrum is the emission, the line spectra is now the absorption spectrum. What is seen will depend on the relative position of light source and observer. So here we have a star which will be sending out a continuous spectrum. However, elements in the atmosphere of the star will be creating an absorption spectrum on top of that continuous spectrum. And here we have a region of very low density interstellar gas. An observer here will see the absorption spectrum due to the atmosphere of the star. When the light from the star passes through the interstellar gas, certain wavelengths will be absorbed by atoms within the interstellar gas and re-radiated in all directions. So an observer here would see an absorption spectrum due to the atmosphere of the star, but also an absorption spectrum due to the interstellar gas. An observer over here would see an emission spectrum from the interstellar gas, as it re-radiates its light in all directions. Incidentally, the observer here would get the same emission spectrum as the observer here, but for this observer, looking at the star, the light from the star will drown out any emission spectrum from the interstellar gas, so it is seen as an absorption spectrum.